Hello friends, I am basically Dsa, a student of second year in Computer Science and Engineering Department of Institute of Engineering and Management, saltlake. So basically, what is my professional background? In 2024, I gave my first JE exam and I scored about 93%. I remember that I scored 93 3.02 percentile in JEE main, and after that in April month in 2024 I gave my West Bengal joint examination and I secured rank basically 4106, and there my marks was approximately yes remembered 77.26. So basically in my second year, what is my experience? Basically I experienced that for in case of placement view, the DSA is more and much more important, and this is the very fundamental aspect of every software engineer, also every students whoever came from CSC and CSC allied branch also. And also I came IEM Salt Lake by WBJE ranking. Whatever college, I basically preferred IEM over any other private engineering college. And also at first I got the leather technology CSC government, and then after upgradation I got IEM CSC in 4106 rank. So let's start today's topic. I I gave a particular overview on a particular topic, that what is basically a red black tree. Yeah. So let us with me, and please I should explain the various aspect also there. So please see and watch it. I sure that you would be enjoy this. So what is basically red black tree? Let's start. So basically we know that BBST, that is, what is BBST? That is, BBST means BBST BBST means balance binary search tree. Okay, balance binary search tree. You know this concept. What is basically balance binary search tree? What do you mean by balance? Particularly this topic, what is basically balanced? Balance means basically that height of the, if a part I have a particular node, if the height of the left subtree and the height of the right subtree, and we get subtract and get we mod value, this, if this less or equal to 1, this is basically balanced. What is binary? Binary means basically there are at least 0 children and at most 2 children. What is the concept of at least 0 children? At least means that there should be present null children, and at most 2 children mean, at most means there should be as more as, but not more than 2 children. That is at most concept. So in case of binary tree, there is also 0, 1 and 2 children. What is search? Yeah, we can know the binary search algorithm, that is basically text time complexity order of log n, where n equal to number of entity in which we can perform the task. Okay, so this is basically order of log n. Basically our topic is red black tea. Red black tea is nothing else, it is a sophisticated BBST. It is a sophisticated BBST. You know this concept, that is red black tea is a basically sophisticated BBST. It is a sophisticated BBST. Yeah, basically you know this the concept sophisticated BBST. Okay, it is a sophisticated basically BBST. What is a sophisticated BBST? Please stay with this concept is very much important. BBST means balanced binary search tree, that we explain here. Sophisticated means that should be in balance in nature, and we also learn how basically this exchange by recolor and also rearrangement. So basically red black tree is basically red black tree basically three scientists basically give us, I recall give us Sedgwick in 1972, approximately 1970 to 72, this range. Okay, these two scientists basically construct the red black tea concept. So why basically I can explain the red black tea, why basically I can explain the red black tea. Yeah, this is one of the most more very important things. Basically you know, basically we shall cover here red black tree because they are much faster on average on insert and delete operation, because they are much more faster than average on insert and delete, than average on insert operation and delete operation. Okay, so what is the definition? Yeah, what is the basically definition? Our topic is basically red black tea, so what is the definition about it? Yeah, red black, so what is the definition about it? The definition is basically red black tea is a BST such that the red black tea is a BST such that each node, it is very important, each node is either color red or color blue. Yeah, each node is basically either color red or color blue. If I explain this, that each node is either color red or sorry, blue node, which is black. Oh. So red black T is a BST that each node is either color red or it is a black. So I know that the black is denoted by the red node is basically this is a red node and this is a black node. Yeah, this is a black node. Okay, so this is a red node and this is a black node. Okay, this is also black, nothing else. This is a blackie. Okay, nothing else. So this is basically a red node, this is basically black node. Okay, so particularly these things is this and this thing is basically this. So be sure, red node is basically, I can denote red node is basically circular and basically black node is basically a rectangular or square, you can say. Yes, what is the concept? So the concept is very important. Each leaf, second option, second condition, this is the basically first condition, this is basically first condition, this is second condition. What is the second condition? Second condition is basically each leaf, okay, each leaf node is should be maintained to be black. It is very important to be black. Black means nothing else. This is a black, just there is a space between this is a black, this is a black, this is a black node. If I doing this is nothing else. Should be a maintain to be a black. Okay, leaf node, and basically each red node has only black children. You understand it? This is the very much important. Means if I have a children, this basically suppose I have a binary tree, basically BBST. What is the concept that each red node have only black children? What is the concept? The concept is basically this: each red node, red means nothing else, just this, sorry, each red node, it has at most 2 children, and that is basically only for those are basically black. These are basically black. This is also black, this is also black, because I can denote it. This is a black, this is a square bracket, this is basically rectangular. So each red node have basically only for black children. It is basically very much important that each red node have only for the black children. Each and every red node has only for black children, and each leaf node, suppose this is basically a tree. Suppose this is a red node has only for black children, so this is not possible. This, but a square node have both possible. That is basically this or this, this, sorry, not this. This is square, okay. This is a round and this is a square. So this has only for this and this, nothing else. This is only for black children. This is a black children, and this is null. Null. This is null. Means this is a leaf node. This is a null. Means this is a leaf node. Nothing else. So here is the very fundamental concept that only for a red node have only black children. Okay, and the square bracket means black, maintained to be black. Now each leaf node maintained to be black. It is black node. So we can say the black node means this black node. Okay, so this is a null, this is a null, this is a null, this is a null. From this this is a null. Okay, so this concept is very important. So I actually denote the black nodes. What is the concept of black height now? What is the concept of black height here? The concept of black height, please. Black height of a red black tree. What is the concept of black height of a red black tree? That is number of each number of each path, number of each path. What is the number of each path means number of black nodes in each path, number of black nodes on each path from the root to any leaf is basically same. This concept is known as black height of a tree. We can represent as that is BH, black height of a tree. Black height of a tree. Okay, yeah. Basically, what is the implementation of a red black tree? What is the physical and what is the basically physical implementation? What is the practical implementation of a red black tree? How can you use it? The practical implementation of a red black tree. Yeah, it is very important. Practical implementation of a red black tree, there is Unix. You know this concept. Operating system basically. OS, data structures, that is basically implementation of a red black tree. So before going further, I have a concept that please give a brief overview to structure a red black tree. We can know this concept that yeah, this is a black node because this is a square, this is a red node because this is a red color in color also, and this is a black in color, and it is a circular now. We have note this law, that is the red black tree is a BST, such that each node is either color red or color black. Each leaf node is should be maintained to be black as null. It is basically as null. Each red node have only black children. You should have maintained these things. Each red node have only for black children. And what, and also this is a property, and also it have a property that you should maintain the concept of binary search tree here. Okay, yeah. So what is the lemma concept of lemma here? This is very important, one of the concept. Any red black tree, T, suppose T has height at most how much? At most how much? Big O of log of size of the tree. This is the concept. Why? I should also explain. Because this is a red black tree, it is a sophisticated BBST, basically balanced binary search tree. So why basically the at most height, at most height will be basically this 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 order of log mod of t. What is the basically mod? Yes, the mod is basically nothing else. Mod of t basically is nothing else size of a binary tree. Why can you say binary tree? Yes, this is also binary tree because red black tree is also binary tree. Okay, so the height basically less or equal to the height basically less or equal to big O of this. Okay, at most height will be this. You should basically clearly understand it. If I draw this, let's draw here. So here I can draw. ठीक है, okay. Okay. So देखो, I can start from here. This copy it. Okay. One, two, three. And basically nothing else. This is basically shape will be this. black, red, red. I can construct this type. Okay. Black, then this black, then this, then see, this is a basically black tree. Black tree has basically two children at most, that is one red, one black. Okay, no problem. It may be black, but I assume it is red. But red has this or this. If this will be given, no, because red has only for black children, so this will be given here. Okay, then against red here, against red here, then against the black is basically here, and the here, and this basically where okay. If देखो, this is the concept. देखो, sorry, delete from here basically these two. So from here basically these two basically occur, this and this, this and this. Then this is a red node only for black children. Okay, this and this, this and this, this and this, this and this. Red node has for only for black children. Red node has only for black children. This and this, this and this, this. Now also connected. Now assume it is a, I assume it is a black children also. So here also you can show that this, this and this, this and this. There is also basically two black children here also. You can say, sorry. Now it will be the whole complete. This is basically null because it's a leaf node. No children will be there. Null, null, null. This is basically null, 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 null. Suppose here I can assume basically nothing else. Here I can assume basically, suppose this is a BST na. Suppose 46. ओहो, सॉरी, बहुत ही ज़्यादा बढ़ा दिया थिकनेस. Here is 46. So less than 46 means basically 28 is here. Here basically you can say 67. You can say here basically 28. Less than 28 it is 5 is also here. And the dekho, the red children has only for black child. Red children only for has black child. ज़्यादा तो 35 ही होगा। नेक्स्ट 67 ज़्यादा 49 ही है। 67 से कम, 46 से ज़्यादा ना 49, ठीक है। उसके ज़्यादा 2 होगा यहाँ पर 25 दे सकते हैं, बिकॉज 25 इज लेस देन 28, तो ठीक है, लेफ्ट साइड ये है। दिस इज बेसिकली concept of basically this concept is basically a red black tree. This is a tree. So what is the black height of a tree? Black height of a tree means, please see it. What is the basically black height of a tree? Yeah. Black height of a tree basically is height of a tree plus 1. That is basically at most value. Yeah. This is equal to basically height of the tree by 2. Yes, height of the tree by at most value of the how many? So now I can assume it. What is the proof by lemma? What is the concept and how can we assume it proof by lemma? So basically this is, that is basically nothing else. How can we concept that, what, how can we assume that how many number of black nodes? Number of black nodes equal to basically h minus 1 by 2 and number of red nodes equal to h plus 1 by 2. Okay, so what is h? H equal to height of red black tree. Okay, now the right subtree x, suppose a right subtree, I have a node x and the right subtree of x is a complete binarity, then obviously the height will be h plus 1 by 2. Okay, this is a complete binarity. Okay, yeah. So the concept is now important, that is how can we basically, yes, this is very one of the important concept, that insertion 83 comma t. I have a tree, how can I insert it? Please see it. Please see. Basically, this is basically 46. This is a 46. This is basically left subtree of this, and this is basically black note, because black child has also black or red child. There is no restriction, and this is basically from this basically, and CSM is greater than 46. This 49, and basically the suppose this is basically nothing else. Okay. So suppose this is basically leaf node. Leaf node basically construct null pointer, and it has basically two black children. Red node has only for black children. This is a black, this is a basically black, this is basically null pointer, this is basically null pointer, both are null pointer. Now if I insert 83,2, how can we insert this tree? This is basically also a BBST or a BST. Suppose it is a BST. So how can I insert 83,T in a red black tree? So the concept is basically there. First this is a 46. Okay. So what is my approach? Yeah. This is basically 1 left subtree, and this is basically 67. 83 is greater than 67. So the null pointer will be eliminated. So how can I do this? 67 is basically 67 here. This is a black. Okay. This is a black. Okay. Okay. Sorry. Oh. 49 is red. Okay. Now if we start any insertion, this key node, this node which I can desire to insert, this is assumed as a red node, a red color node, means 83 is very 83 is circular. Okay, then I this denote this, and this is basically both has basically key what squares, black children, black means square in a red black tree, null, 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 null. They see that here basically this will basically insert. देखो, that is insertion of 83 as a red node. Whether there is basically specifically saying that please 83 as a red node. Yes, if we insert any node, this is basically insert as a red node. Red node means circular. What is the concept? Yes, the concept is very important. Yeah, the concept is basically create 83 as a red node, search and insert. This is the concept for insertion. Their similar technique will be applied by the opposite for deletion. Okay. Yeah. What is basically color imbalance technique? One more important technique is basically color imbalance. So color imbalance. Yeah, suppose I have a node that this basically is a node, this suppose this is a left subtree height of 1, this is a 67, okay, this is a 49, obviously 67 is less than 49, so left subtree जो value होगा वो is less than the key value at that node value. This is basically 83, suppose this is basically null, null, and this is basically nothing else, this is basically null. So here is a basically color imbalance. Basically if I insert a node, there is a basically color imbalance. Basically insert 54, insert 54, this is a red. How can I do that? This tree. So doing this is very important. This is basically, sorry, this is basically 46 is basically less than, okay, so 46 is 46 black node, this is basically 1, and this is basically this, sorry, so for 54 मेरे को 54 इंसर्ट करना पड़ेगा ना, तो यहाँ पर तरह एक सेकेंड ये वाला तुम हटा दो, बिकॉज यहाँ पर 67 है तो 67 ही रहने दो, यहाँ पर 67 ही होगा, 67 is basically here. Next 54, 54 means this is basically 49, and this is basically 54 is basically 49 से ज़्यादा 67 से छोटा, तो यहाँ पर ही होगा एज अ रेड, ओके, रेड, ओके, if somehow यहाँ पर जो 49 if it is basically becomes red, if the 49 is basically becomes red, if we insert 54 then it will be like this, 49 becomes red, and red we can already know that red nodes have only black children, so 49 here should be black, 49 here should be black, okay, 49 here basically should be in black, so 49 black red children, okay, 54 this, 54 this is basically null, this is basically null, 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 black children, this is basically here 49 is red, but this is basically 49 is black, this red 49 change here red black, this 49 change here in 49 black, this 49 change here basically 49 black, not red, so as this is now black, the red node have only for black children, so it is Okay, this is basically 83. Here is basically as a black children. Okay, and it has basically also two null children. Null node basically is basically black, 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 black. So this is basically color resolution tips. Basically, the topic is basically here this. This is a concept. Make 49, make 49. This 49 is basically red here. Here basically 49 is red. At first 49 is red. Here 49 is basically black. Black. Make 49 is red to black. Then what is making 67? Making 67. Making 67 red. Okay. Okay. Now, yes. If this is red, red node have no red children. So this is a basically contradiction. So for this also be a black. Okay. So this is basically it is a red. This is a red. At first this is a red, and this is a black. Okay. When I solve this problem, there is a error for myself also. See, this is 67 is basically black, this 49 is basically red, so this is circular, this is rectangular 67. Now when I change, and for color imbalance thing is when I insert this 83, when I insert this 854, sorry 83 is here is 83, when I insert this 54, when I insert this 54, when I insert this 54, for for this for this for this insertion, this 49 is transformed to 49 black, and where the 49 is red, this will be transformed 67 black to red. So making 67 black to red, black to red. Now 67 red has both black children. Okay, this is also black, this is also black, this is also black. Okay, this 49 is basically at first, this 49 is at first basically red, now it basically black, and this 67 is at first black, now it is basically 67 is at then red, and making 83 black, तो black ही होगा, making 83 black. If somehow this will be red, then making 83 is black, because the red child have only for two black children. This is basically resulting T now. At first this is basically resulting T from this. This is basically insertion of 54. Insert 54. Yes. Okay. So this is my basically first video. I know that